Hello and welcome back. Today I will continue working on the Class B amplifier build. Designing it took a bit too long, so I left the measurements for today. So I will be checking how the circuit works, look at some of the signals passing through it, the efficiency, and some other things. Now, before getting started, I would just like to point out that the design in the simulator had a voltage gain of 2. And the signal coming from a signal source with 50 ohm impedance into a 50 ohm load gets halved. So half times 2 equals 1. This thing didn't really turn out to be an amplifier. The nice way would be to call it a buffer or a repeater, but it's more like a distortion machine, as we'll later see. So if you're curious about that and much more, then keep watching. So without delaying things too much, here is the final schematic that I ended up building. So here on the top side we have the schematic that we've simulated. So we got our input signal going through the phase shifting transformer, the 25 ohm loads, AC coupling into the transistors, we've got our trimming potentiometers, and then the output transformer going into another connector. And other than this, I also added, as always, an input filter, so a supply line filter, to prevent any noise going out onto the supply lines. And if we quickly look at the layout, so it's decently small board, 4.5 by 5.5 centimeters, and the reason why I left the resistors in the emitters is to get a nice and symmetric layout. So you can see the battery line coming in through the middle of the transformer, then the two windings to the left and to the right going to the collectors of the transistors, and then the emitters close with resistors to ground. So having separate emitter resistors makes the layout nice and, well, symmetrical, as well as allowing lines to supply the circuit. And well, other than this, we have the trimming potentiometers and then the input signal. So now let's see how this thing turned out in real life. So here is the final board. The input phase shifting transformer is built on a toroid core with the twisted pair of wires, and the output transformer is built on an E16 core with the windings interleaved. So first I called half the primary, then the secondary winding, and then on top of this the second half of the primary winding. Now, considering the output power, the transformers are quite oversized. You can use far smaller ones for just half a watt. But these were some of the cores that I already had lying around, so I used them. And well, other than the transformers, we can also clearly see on this side the two trimming resistors, with which we can adjust the bias point and the operating class. So, first things first, does the circuit work? So I prepared the setup right here. I'm supplying the circuit from 20 volts through a milliamp meter so we can accurately measure the current being consumed. And then the circuit is getting an input signal coming from the signal generator and an output signal going into a 50 ohm load. And this output signal is measured on the yellow trace and the input signal is measured on the green trace. So the very first observation regarding the circuit is that even though there's no input signal or output signal, we do have a current consumption. So we have about 6 milliamps. So is this normal? I mean, working in Class B, should we be getting this sort of current? Well, as it turns out, we are not getting any current running through the collectors of the transistors. All of this current is passing through the bias setting network. And I know for a fact that the current is not going through the collectors of the transistors because the trimming potentiometers are set to 0 ohms. So the bases of the transistors are short-circuited to ground. So based on the bias setting resistor values chosen, we will get this sort of static current. So first thing to do is start setting the trimming resistors to a value so that there's just a bit of current going through the transistors. So if I increase the value of one of them, at some point we should see a bit of a variation in the current consumed by the circuit. So as you can see, it's slowly going up. If I go higher, we'll see a steep increase in current, taking the amplifier into Class AB. But we'll just want to leave it somewhere on the edge where the current just slightly increases. So let's say at about 5.9. If we now also supply an input signal, we see a nice sine wave input signal, but the output is only half of a sine wave. So only half of my amplifier stage is amplifying at the moment. So next, I will be also setting the current through the other transistor so we can get the full picture. So here again, I'll increase the value until we just see a slight increase. So let's say somewhere around here. So now if we run the circuit, we see a complete sine wave being generated on the output. We see minimal crossover distortion around the 0-volt point. And well, this is normal. We could set a bit higher currents through the transistors and then this should go away. So if I add just a bit more current through each of the transistors, we're taking the amplifier into class AB, and we now see very nice, very clean transitions. So now let's take it back to class B though. So just a bit lower. So the circuit seems to be working. One final thing to test though is its efficiency. So right now we can see that we have 6.7 milliamps running through the circuit when there is no signal, and when we do get a signal, we are getting a 5.04 RMS voltage into a 50 ohm load, and the current being drawn is about 44 milliamps. So this is giving us an output power of 516 milliwatts and a total efficiency of 58.6%. Now, if we would be subtracting the current used by the bias setting resistors, so just to look at the efficiency of the output stage of the transistors and the transformer, so we subtract from this 4 milliamps the 6-7 milliamps that we're getting when there is no signal, we are getting a much better efficiency of 65.7%. So the amplifier works just fine. Next, we can have a look at the signals passing through the circuit, specifically the phase shifting network. So right now I have it set up so that in green we have the input signal, yellow is the output, and then the blue and pink ones are the two signals going into the bases of the transistors, so the two out of phase driving signals. And right now, with the signal generator set to 400 kilohertz, we can see that the meter is giving us 180 plus or minus degrees, so almost perfectly 180 degrees out of phase signals are driving the output, and the output is quite clean. Now if we play around with the frequency, specifically go lower, so 200 kilohertz, 100 kilohertz, we still have a decently good phase shift, so it's rising up a bit, so 182 degrees right now. But if we go even lower, so we have about 185 degrees of phase shift, 5 degrees more than the 180 that we should be getting, so just like we've seen predicted by the simulator. And we can also see this uneven distortion in the output signal. So as you can see, the rising edge on the output is perfectly clean, it's perfectly straight, but on the falling edge we have this dent appearing. So this is caused by the two signals being out of phase. And well, the lower you get, the worse it becomes. So right now we're at 10 kilohertz, 190 something degrees, so more than 10 degrees away from what we should be getting, and this glitch is becoming more and more obvious. So as long as the working frequency is high enough, the circuit will behave correctly. Next, let's see the overall frequency response of the circuit, so regardless of any sort of distortion. And for that, I set up the oscilloscope and signal generator to work in Bode plot mode. So if we run the measurement, this will measure the response of the circuit, so input to output ratio, starting from a frequency of 10 kilohertz up to 50 megahertz. So you can see the complete bandwidth and the response that this amplifier has. So I set it up so that we have 1 decibel per division, and we can see that we have a fairly flat response of about 4.85 decibels, so it's not really 6 decibels, starting from a frequency of 63 kilohertz and going up to around 2-3 megahertz. And after that it drops off. But the -3 decibel point is somewhere below 10 kilohertz and somewhere at around 10 megahertz. So the amplifier has quite a wide bandwidth regardless of the performance of the magnetic cores. So you can see that the response is not very flat, so the magnetic cores do have an impact in the behavior, but regardless, we do get a wideband response. Next, let's look at the distortion of the amplifier. And based on popular demand, I will be looking at two different types of distortion: harmonic distortion and intermodulation distortion, since these two are quite different and need to be handled differently. So, as setup, the signal is still coming from the signal generator, but to measure it, I prepared the spectrum analyzer. And first things first, we need to check that the signal source is not distorted. So it doesn't matter how good your amplifier is if the initial signal is already distorted. So to measure that, the signal coming from the signal generator is passing through a 10 decibel attenuator and then going into the analyzer. So if we turn it on, I'm injecting an 100 kHz input signal, and we can see that there are a few harmonic peaks. So these are peaks appearing at frequency multiples of the initial signal, so 200 kHz, 300, and so on. But these are, so this one is at 6 decibels, next one is at about minus 4.3, so about 50 decibels in between the peaks. So if the amplifier has 50 decibels, it's coming from the generator. If it has a smaller difference, then it's coming from the amplifier. So now let's connect the amplifier in. So now I connected the amplifier, and if we apply the same input signal, so it's a 5-volt peak-to-peak signal coming from the generator, we can see that we are getting quite a bit of distortion. So we see our initial fundamental peak, and then the next one is just about 10-15 decibels lower, so quite well distorted. Now what we can try is reduce a bit the amplitude of the signal that's being amplified. So now I went to a 1-volt peak-to-peak signal, and we can see we have a much larger difference in between the first two peaks. So now we're up to about 25-30 decibels. So one way of improving the response of your amplifier is by reducing the signal amplitude a bit. Now, the other type of distortion that we want to look at today is intermodulation. And for that we need a slightly different setup. So again, I've connected the signal generator, and for this test we don't just need a single sine wave with a single frequency, we need two sine waves with close frequencies. So I have a 100 kHz sine wave and one at 105 kHz, so there's only 5 kHz difference. And ideally, what you want to see in the spectrum is only these two spikes and nothing to the left and to the right. So right now with the signal generator by itself, things are working as expected. Now I connected the amplifier, and if we generate the two signals, well, this is something you don't want to see. So we see our initial peaks that are being amplified. There's probably harmonic multiples of these at higher frequencies, but that's not really what we're interested in. What we also see and what we don't want to see is these extra spikes appearing to the left and to the right, which are appearing at equal frequency distances as the two peaks are. So there's 5 kHz in between the two peaks. The second one is at 105 kHz. Next spike is appearing at 110, so 5 kHz more. Next one 115, and so on. So other than the two fundamental signals, we are also getting extra signals at frequency intervals equal to the difference between the two initial signals. Now again, one thing that you can try to do is reduce the amplitude of the signals, so to try to get the amplifier to distort a bit less. And the other thing we can do, which would also work for the harmonic distortion, is to play around with the amplifier class. So I marked out on the potentiometers where exactly class B operation is, so the one that we set earlier. And if we play around with this, we should take the amplifier into class C or class AB. And we will also be able to see this on the current meter. So if I reduce the bias point, see a decreasing current, so we're going into class C now, we can see that we still are getting our amplified signal, it's still getting amplified, but we're getting a much clearer distortion spectrum. So even though class C is more efficient, it's far more distorting. On the other hand, if we go the other way, go towards class AB, we get a slightly higher current, but a cleaner spectrum. So we can improve the response by setting the bias resistors a bit, but we can also try to reduce the amplitude now, and we have an almost clean spectrum. So it's not perfect, we still get these harmonics appearing, but it's far better than what we started off with. So the main difference in between intermodulation distortion, disting, and harmonic distortion is that if you want to filter it out, for harmonic distortion, well, you can simply put a filter that will relatively filter out anything above your useful frequency, so the precision doesn't have to be that big. But with intermodulation distortion, the unwanted noise is very close to your useful signal. So here you will need much better quality filters to be able to handle this sort of noise. So if this is the sort of problem that you're trying to deal with, it might be good to transition from class B to class AB. Even if you're sacrificing a bit of efficiency, you will be reducing quite a lot of noise. Now, distortion is not just related to the amplitude of the signal, it's also related to the frequency of the signal. So I set up the amplifier again with the oscilloscope and it's set back into class B operation. And right now we have a 300 kHz signal passing through it. And we see that there is a bit of distortion at the ends, but other than that the signal looks pretty decent. But now if I increase the frequency, so right now we're at about 800 kHz, still looks relatively the same. But at some point we start to see this edge change its shape. So right now we're at 1.4 MHz, and if I go even more, we can see this distortion moving around based on the frequency of the signal. And well, if we go even higher, at some point we get all sorts of weird effects going on. So even though the amplifier can amplify up to about 10 MHz, the higher the frequency, the more effects and artifacts that will appear in the signal. So it's important when you're testing your amplifier for distortion to not just look at one frequency but at multiple frequencies. Preferably at your extreme frequencies and maybe one or two in the middle of the usable bandwidth. Now let's look at some modulation behavior. So we've already seen that the amplifier has a very wide bandwidth, so frequency modulation should not be an issue. But if we try out some other things, for example amplitude skip keying, here we have very short pulses, and we can see that the amplifier is, well, first of all, inverting the phase, but secondly, it is responding very well, very fast to the input signal. So there's no delay between input and output. And also full amplitude is reached instantaneously. Another thing we can look at is phase modulation, so when the input signal suddenly changes phase, and again here we can see that the output very quickly follows the input. Now granted, we do see some oscillations appearing. So with this sort of very sudden change you might run into some issues, but nothing that a bit of filtering can't handle. Now, final thing to look at is the thermal behavior of the amplifier. And for this particular amplifier, it's important to look at the two operating modes, with and without a signal, since some power is being used in both modes. So right now we have no input signal, no output signal, some current is still being drawn by the amplifier. And if we check it out, so first of all from the top side we can see that there's a bit of heating from the other side of the board. We'll look at that in a moment. But we can also see that the two transistors are not very cold. So specifically the one on the left is quite warm. So most likely the problem here is that I didn't set the potentiometers very well, and there is a bit of standby current on the left channel. If we have a look on the back side, we can clearly see our bias setting resistors are heating up. So those are the only components that are warm when there is no signal. Now on the other hand, when there is a signal, so right now we have quite large output signal, 40 something milliamps being used by the amplifier. Part of this is going of course into the load, but the rest of it is being dissipated on the amplifier. So now we can very nicely see the transistors are the hotspots of the amplifier. So especially on this side there's not much else that's heating up. And on the other side we have now the bias setting resistors as well as the emitter resistors heating up. So when the amplifier is operating, we have more components that are dissipating heat. In the end, the circuit works decently, even though better performance could have been obtained by a better choice of transformers, both the magnetic cores as well as the exact topologies used. So you don't really see the one-to-one bifilar wound transformer together with a center tap transformer in the same design. Usually it's just one type of transformer or the other. And well, when you combine the two, you get what we got today. But regardless, even a circuit that does not work well is something to learn from. There is quite a lot of value in understanding the underlying details. And with that said, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my videos, and see you next time. Bye bye.